So yes, today I'm going to talk about value-free concurrency in Rust. Before starting my talk, I want to say thank you for Mate and Elon because they reviewed my presentation and talk. And also I want to say thank you to Lovebase for providing such a great venue. And I'm so excited to be here today. And a bit also feel nervous because this is the first time I give a presentation in English. So yeah, let's see how it goes. So yeah, there is no introduction slide. Oh, but okay, yeah, I'm Motoyuki from Tokyo, Japan. And so I'm currently working for CyberAgent Inc., where I'm developing digital signage systems in Rust. And also I'm active to the open source project. So I'm currently one of the, I would say, organization member for Tokyo project. So if I have free time, I try to contribute to the project, like fixing bugs and submitting an issue and I don't know, reviewing a pull request. And yeah, I'm doing that kind of things. And one thing I want to make here is that actually Tokyo has a lot of crate, just other than Tokyo crate itself. We have tracing crate or Tokyo console crate and or bytes crate, and more importantly, Loom crate I'm going to talk about today. So Loom crate is a testing library for concurrent programs, and it has additional very interesting features where, so by using Loom, we can explore all possible program states. So by using Loom, you can explore all possible execution paths and like check if there's subtle bugs or not. I think this is a really cool feature. And it's kind of importantly, and if you go through the Tokyo project repository or issue tracker, probably you'll find a bunch of comments saying, like, hey, can you add a Loom test for this new feature or things like that? So yeah, Loom is used heavily in the Tokyo project. So like I said, Loom is heavily used in the project, but I rarely see the usage outside of Tokyo. So today's goal is that I want to introduce the crate and let's see how it works and how it looks like. And furthermore, I want to dig in the crate itself because under the hood, behind the scenes, it uses really interesting technique, which is kind of like formal verification kind of stuff. So, like specifically, I want to give you a basic idea of model checking, which is Loom used behind the scenes. And so Loom uses one specific technique called dynamic partial order reduction. So I will cover that as well. And hopefully, if time permits, I want to also cover how Loom handle memory order. Yes, yeah, let's get started. So today's talk is about multi-thread programs. So let's talk about first. So today, 2024, whenever we want to build a high-scale systems, it's really important to understand how multi-threading program works. But at the same time, it's kind of difficult to build it correctly. So some of you may imagine this kind of image, like this is taken from the model memory order documentation from Rust documentation, or there's even this kind of paper saying that analyzes the complexity of the concurrent program. So why so hard? Well, I think there are many factors for this, but the majority of the complexity comes from this, like non-determinism of thread scheduling. So if you run the multi-thread program, behind the scenes, your operating system constantly switches your thread. And actually, that increases the possible cases of that program. So like whenever we try to analyze that program, sometimes it could be difficult because there are so many cases we have to care about. So who can help us? We need to have a way to overcome this complexity. So this meetup is Rust meetup. So how about Rust? Because Rust is known for its safety guarantees, and also we have this really cool trait, send and sync. So in Rust, we can add additional properties for our own type. So like if this type, our own type is safe to send another thread, we say, okay, this type is send. And or if this type is safe to share across the thread, we say this type is sync. So because Rust itself has its own properties around the concurrent safety, Rust sounds really promising. So even with Rust, we sometimes see this kind of issue saying, hey, we need to have a way to detect the drug for futures mutex and things like that. So this means that even with Rust, so Rust's type system can prevent certain kinds of problems, but even with Rust, we still have some problems and concurrent related problems. So are there any good way to find subtle bugs that Rust could not find? So by the way, we can get inspiration from this talk by John, who is, I think, one of the most famous Rust YouTube streamer, I would say. And I like his videos, by the way. Anyway, in this talk, he says that being exhaustive is really effective or a good way to deal with a program with high possibility or high cases, such as concurrent program. So what is an exhaustive way? What does this mean in this context? So in this context, exhaustive way is a way, like instead of testing a limited amount of cases like traditional unit testing, but instead try to explore all logically possible execution paths. So exhaustive way means that. But is that possible? It sounds really complex, but in fact, there is some effort or research is going on around this area. And as far as I know, there's broadly two categories, and one is called theorem proving, which is a method, way to test a program similar to how math proves the mathematical propositions. So tools like Coq or Agda or Ring could be considered as a theorem proving. So on the other hand, model checking is another way which try to translate into the program to another sort of state transition graph, and then it try to explore all possible execution state. So tools like TLA Plus or Loom, I'm going to talk about today, is considered as a model checking. Okay, so far we've seen background around Loom. So now let's look at the Loom documentation. So this is taken from the Loom's great documentation, and it says it runs a test many times, permuting the possible concurrent executions of that test under the C11 memory model. It uses state reduction techniques to avoid combinational explosions. Well, there are many important keywords here. But in summary, like I said, Loom explores all possible permutations of thread scheduling. And more specifically, behind the scenes, it uses DPOR, which means dynamic partial order reduction. And this is a model checking techniques. And yeah, like I said, it's used in many places in Tokyo. So yes, I think I covered the basic background or history around Loom. So now I want to show some real code example and let's see how it looks like. Okay, so here is a simple Rust multi-thread program. By the way, I will heavily use this example in the later slide as an example code. And yeah, so in this program, so there are two atomic variables here, which share the same inner value. And then next, we span the thread, and then in the span thread, we do this v1 store, and then, oh, this is commented out. And on the other hand, on the main thread, we do some sleeping, and after that, we roll the v2 value, and finally, assert the value is equal to 1 or not. So let's see what happens if I run this program. Okay, so now program is, oh, thank you. Thank you. Now program is success. Thank you. And but what happened if I commented out this thread sleeping? Let's see what happened next. So now test. So now test is failing. So maybe some of you may realize the cause, but so in fact, this test sometimes fails because there is no guarantee that this load operation happens after this V1 store operation. So because of this, we sometimes see the test failure. So because this test itself is kind of simple and it's relatively easy to find, but let's imagine if you have 100 or 1,000 lines of code and span much many threads, that would be much more difficult to find this kind of bugs. So this is exactly the place Loom comes into play. So this is a Loom version of test. The program itself is the same, but there is also important differences. The first, we have Loom's atomic variable, and Loom also expose threads or sync APIs. And finally, we wrap our whole program by this Loom model function. So by doing this, now Loom can check if Loom will explore all possible execution paths by running this test program multiple times. So let's see what happens. So yeah, now it test is failing, and notice that in this time I don't include any sleeping. So because Loom supports deterministic execution, so whenever we run the program, the Loom will output the same result unless we change the program content. And I think this is a cool feature. And I want to do one thing more, and so So like I said, Loom tried to run program multiple times, and you can that fact by including this print statement. And if I run this program again, so now we have 5 hello output. So this means that Loom now think that, okay, to analyze this program, we have to execute this program 5 times to explore all states. So yeah, this is kind of interesting to see. Okay, so this is the demos I prepared. So let's back to the slide. Okay. So yeah, this is the half part of this today's talk. So at this point I want to hear the question. So are there any people who have? Yes.
Has anyone tried exploring the use of Loom outside of testing?
Yeah, that's a good question. I'm not sure. So at least as far as I know, the use case in Tokyo is just testing purpose. So I don't know any cases where like Loom is used as a general purpose. Yeah.
How much is Loom impacted by standard arc, or the result of Loom? How much is it impacted by standard arc, standard thread? And if I use it in my labs or in third-party labs, how much is it impacted? So the Loom result.
So your question is how API, what kind of API is supported by Loom?
No, I mean the Loom test result. How much is impacted by using third-party arcs implementation or thread implementation, or I mean Loom implemented all this and you use it already in this test, but how much is impacted if you use a standard arc or a standard thread or from another third-party library thread, the implementation, how much is the result of Loom impacted by that? Impacted.
So Loom, so probably I'm not sure I understand your question properly, but so what kind of
I think he's asking if the result would be different if you used some third-party library that implements its own arc.
Oh yeah.
Is that your question?
Yeah, exactly. That's my question. How
Yeah,
much is it impacted?
Yeah.
How much different is?
Basically, Loom's arc are based on standard libraries one. So yeah, I've heard of there are another arcs implementation out there, but yeah, I believe that Loom's arc is based on standard libraries one.
For example, we have these libraries who implement these asynchrone, how's it called again? Mutuals, the asynchrone mutuals, right? These libraries will implement asynchrone mutuals. And how much would the result of Loom impact?
Mutex.
Mutex, mutuals. So there are synchrone mutuals there, but not implemented by standard, but by different third-party libraries. So, for example, Tokyo and others.
Yeah. Tokyo has its own mutex. So it's kind of complicated. So Loom is used to test Tokyo's mutex, but Tokyo's mutex is completely different from the standard library because it's async API. So yeah, but yeah, like you said, Loom is used to test like Tokyo's mutex or reader writer rock or even runtime internal scheduler testing because it's pretty complicated. So yeah.
Okay, thank you.
Thank you.
Next.
Continuation of the last question. Can you go back to the code, please, for just a second? The code you showed earlier. Hi, can you? The one where you actually showed using Loom to verify a program.
So, sorry.
The code where you actually showed how to verify a program using Loom. Can you go back to that one, please, for just a second?
Okay. I guess this one. Oh, this one. Sorry.
Right. So this one, it's not clear which arc you're using here right now, which arc, which atomic use size, and so on and so forth. If you were to use just the standard library ones, would you still catch the same bugs, the same problems that you would catch if you used Loom specific, like structs and enums and so on and so forth types? Is what I was curious about. I think that's also what the question from before was going at. Like, because like, if I write a library, I'm not gonna, I don't really want to do like an import switch for every single like dependency that I have on every single like import to have like only for tests have the Loom one and instead for everything else have the standard library one. So I need to, like, if I'm going to use this, I need to actually be able to use this while relying on the standard library arc and mutex and so on and so forth. So would it still like give me an error like it should if I use the standard library once?
So if you use standard libraries one, Loom doesn't work really well because so behind the scenes, Loom's arc try to hook the arc's execution and doing some hacks behind the scenes. So if you don't use the Loom's arc, there's nothing happens.
So what that means is like, if I want to test my library with this, I need to like switch my imports during tests, like so, doing like an if config test or something like that.
Something like that. So you have to switch your arc. Yeah, that's true.
Okay, thank you for answering.
Following that question, actually, so we only really need Loom's arc for the testing, right? And our regular code, we would still use the standard library arc. Or do you need to use Loom's arc in your actual code?
So I don't know much example, but in Tokyo, we use CFG, like I said, and so we try to test the Tokyo API, even if we try to use that API as a Loom test. So
so maybe when you say CFG, you mean the conditional compilation macros?
Yeah. So for example, if Loom test flag was passed, and then we're gonna use Loom's arc, and then otherwise we're gonna use standard library's arc. So there is such a I don't know group code in the code base. Does it make sense?
Ah, yes. Thank you.
Thank you.
Thanks. Do you feel like Loom lends itself well to being applied in larger teams?
Yeah, I think so, but I will cover, but there is still some limitation. So I show this arc and sled APIs provided by Loom, but still there is no equivalent. Some API lacks and the standard libraries API. So yeah, there is still some limitation, but yeah, I think you can try and apply your team or whatever. Yeah.
So far, from what I've seen, it sounds like it's better to work on solo projects where you're doing unit testing by yourself.
Yeah.
But hey, thank you.
Yeah.
Earlier you mentioned the theorem proving languages and model checking languages, and specifically TLA+. And I've checked out TLA+, and one of the more interesting things about TLA+ is that you get to continue the execution. Well, although it's a mathematical formula, but you get to talk about like the continuation of the state up to like until the model checker decides it's done enough iterations, right? So you can actually check for not just whether a single short thing happened, but like does it continue to work until like for as long as you like. So that's like checking for invariance and liveness guarantees, what they call it, like whether it invalidates an assertion and whether you're actually making progress, which is kind of hard to describe, but are there things like that that help you describe those properties within Loom?
Sorry, I'm not sure.
Okay.
I will cover the internal later, but
Sure.
Loom just try to run the program multiple times, and I don't know there is such a complex way in the room. So yeah,
I think we can move on.
okay. Thank you for a lot of questions. Yeah, so I think we can. We could end the presentation at this point, but maybe some of you may be interested in how Loom works under the hood, like I was. So we're engineers, so let's dig in to figure out what's going on behind the scenes. So this is a Loom documentation, and there is actually useful tips where to refer if you are interested in the internals with the links to the paper. And interestingly, I had to read through these 3 papers for preparing my presentations. And yeah, this was kind of challenging, but at the same time, it was a bit fun for me. So yeah, so so those who are scared by previous paper image, don't be afraid, because I'm not expert either. So in the rest of the talk, I will cover the Loom internal, how Loom works behind the scenes, but I will not try to dig in too much detail, but instead I try to give you the basic idea of the technique. So yeah, let's get started. So the rest of the talk is somewhat unrelated to Rust itself, but it's more about model checking itself. So first thing we have to do is we have to consider is that how to explore all program states. Because remember, model checking is a way to translate the program into some sort of state transition and then explore all states. So we need to have a way to do that. So here I want to define state and transitions. So let's say we have program has state S called S, and then let's define the transition as transition that changes the state from one state to another state. So we can think of states such as program's local variable and things like that. And we can think of transition as like each lines of code, because each lines of code do something that could change the state from one state to another state. So let's see this simple program, and like this is almost the same example as I showed in the previous demo. And I changed slightly, and I picked the most important part, which is a multi-thread involved. And so yeah, so this is a diagram that represents state and transition concept of the previous example, the previous program. So let's say we have initial state S0, where nothing has happened. And then what happened next? Well, because we have 2 threads, we have 2 options here. So change to the thread 1 or thread 2. So if you execute thread 1, we're going to do v1 store, and if we choose thread 2, we're going to do v2 row. And what happened next? So on the rest side, because we have executed all tasks in the thread 2, we don't have any task in the thread 2. So therefore, there are no additional branches here. So thread 2's task is just one v1 store statement only. So on the other hand, on the right side, because we executed v2 load first, there are still more than 2 options, and so therefore we have still 2 branches. So by doing this, we can build this kind of state transition graph, and then by visiting all of the branches, we can check if this program has saddle condition or saddle bags. So yeah, all we have to do is just search all for permutations, and I think this method itself is not so complicated. But if you're gonna do like simple math, probably situation is not so good. So let's say we have 10 lines of code and 2 thread program, and if we apply previous method to this program, probably we have to run the program 1,024 times, because for each line of code we consider the threads will switch or not. So if we increase the lines of code, the cases we have to explore will be gonna be very big number. So yeah, unfortunately, this way doesn't work really well in the real world code. So we need to have a way to overcome this. So instead, so let's say we have this kind of graph, and instead we try to visit all of these branches. We want to do some cheating and skip some identical graph. So this is a basic idea. And this is exactly the place where partial order reduction is called and comes into play. So back in the day, researchers have found that usually program has several semantically identical transitions. So they try to reduce the state transition by introducing the dependency concept. So what is a dependency? Well, dependency in this context is a way to tell like 2 operations are independent or dependent, like as word suggests. So more specifically, if reordering the 2 operations does not change the program's final state, we say those 2 operations are independent. So for example, reading from the thread local variables could be considered as independent operations, because usually just reordering this thread local operation does not change program's final state. On the other hand, there's also dependent operations. So for example, acquiring a rock from the mutex could be considered as a dependent operation, because reordering these operations could change the program's final state. So let's feel the dependency concept by, again, using this simple example. But this time, I add additional statement, simple print ln statement. So let's see, reordering this to print ln operation changes the program final state or not. So if you think about it for a moment, probably you find that just reordering does not change the program's final result. So in that case, we can say these 2 operations are independent operations. So next, let's see how this dependent concept can reduce the actual state space. So this is a diagram, state transition diagram that represents previous program. And so interleaving, so there is also two paths where just two println execution is reordered. And in the previous slide, because we confirmed that just reordering does not change the program's final state, we can say that these two paths are semantically same. And then finally, we can skip one of them. So this is the basic idea of the partial order reduction. Because the program itself is pretty simple, we cannot feel the powerfulness of this method. But in the real world program, it can reduce tremendous amount of states needs to be explored. So yeah, let's talk about a bit different ways and dynamic partial order reduction. So this is a bit different from the partial order reduction itself, but Loom actually uses this one. So historically, partial order reduction was a static analysis method. So, but it turns out that doing checks while runtime is much more efficient. So DPOR tries to check the state space at runtime, like while executing program. So just hearing the explanation would be, I think, it's a bit complicated. So let's see again this explanation, and let's see what's going on in the DPOR. So DPOR try to run program multiple times. So let's say we execute first execution, and now we are on thread 1, and we also have initial set S0. So let's say we hit the dependent access, as I mentioned. So this is like something like reading from atomic variable or mutex value. And more importantly, dependent access is a place where we have more than two thread interleaving options. So in this graph, we have an option like switching thread 1 or switching to the thread 2. So what algorithm gonna do next is so first, whenever we hit the dependent access, we store the state S1 to some sort of data structure. So in this case, stack. And the next, we will choose one option. So in this graph, we choose thread 1 and keep executing. And then program proceed. And let's say we have additional dependent access. So in this case, we again, we store the S3 to the backtracking point list, and then choose one of the options. And then program ends, and this is the first execution. So at this point, notice that we have two elements in the backtracking point list. So we need to explore all backtracking point lists. So we proceed the second execution. So in the second execution, we pop the head element, so in this case S3, and then we proceed the program to the S3. And then when we hit the S3, we will make a different choices to the previous one. So in this case, we will choose thread 3. So second execution ends, and this is the third execution. So we still have one element in the backtracking point list. We have to do third execution, and in this case, we have S1. So when we hit the S1 state, we will choose a different options. So in this graph, in this case, we will choose thread 2. So by doing this, we can explore all of the program states or interleavings. And this is something like backtracking or depth-first search of data algorithms. Yes, and so in summary, so if you find a state that needs to be explored, add that state as a backtracking point list at runtime, and repeat the program until all backtracking points are explored. So, and I have additional demo, but is there time? Okay. I originally prepared another demo, but this time I will skip this part. Okay, this is the last topic. So DPOR sounds good, but if you look at the Loom documentation closely, you find a word of memory ordering. So actually, Loom can handle subtle read result caused by memory ordering. So let's see how Loom handle this complexity, additional complexity. So, so memory ordering is, so let's recap the memory ordering. So memory ordering is the rule how memory operations are executed and observed in the concurrent systems. So previous methods, DPOR only takes into account the sequential execution model. So, but in reality, in the real C or C++ code bases, there are much more complex read result caused by memory ordering. So we need to have a way to handle that. So again, let's see this example and to how Loom handle the memory ordering. So let's say we execute a thread span, and also we've done on the thread in execution v1 store, and so on the main thread, let's say we execute v2 road. So what kind of value this road could be? So, well, we could see both 1 or 0, even if the v1.store has already finished. So this is because we use relaxed ordering here. There is no guarantee that v2 road can see the v1 store as a result. So this means that we have additional possibilities for atomic memory ordering read operations. So the algorithm I introduced previously should explore all possible road results. So this sounds a bit complicated, but by extending the previous method, we can apply our algorithm to handle this memory ordering complexity. So this is again DPOR graph, and so let's say we hit S1 where read but involving memory ordering. So in this time, we also not only store to the backtracking point list when there is a dependent access, but instead we also track the read operation of memory involving memory orders. So by doing this, we can naturally extend the DPOR algorithms to adapt this memory ordering complexity. So yeah. Oh, sorry. So to handle the memory model, we particularly pay attention to read operation. And more specifically, in addition to DPOR's thread execution backtrack point, roll results selection will be also considered. By the way, if you want to recap the memory ordering or thread API kind of stuff, I would recommend this book. This is really detailed, explained, book, and I would highly recommend read this. And yeah. Okay, so this is almost all I prepared. So if you want to know more about our Loom, there is some materials that explain better than me. So there is 2 papers I refer when preparing this presentation. This is a paper that introduced dynamic partial order reduction. So Loom heavily rely on this paper's content. So, and also there is another paper that based on previous DPOR paper and discuss how to handle memory ordering, like I said. So nice thing about this paper is that actually there is a GitHub repository. So if you're interested in the implementation side, you can refer that. And yeah, so it'll be really cool if you're interested in Loom by my state talk. So I think Loom is pretty much mature at the same time, but there is some Loom needs to be improved. So when I look into the implementation, I see a bunch of to-do comments. So I think implementation could be much more improved. So second one is, like I said, there are many unimplemented types or thread standard library thread APIs or atomic variables APIs. So we could implement that one as well. And I think almost all open source projects have the same problem, but there are some pending PR. So actually, this is one of the reason one of the motivation of today's talk. So I want to just understand the Loom internals. So yeah, I think we need more reviews, I think. Yeah. And so last one is that Loom is currently executes on single thread. I think this is not so efficient. So it would be cool to, it would be cool if we could run Loom on the multi-thread environment. And yeah. Yes, that is all I prepared. So thank you for listening.
Thank you. Thank you so much. So we don't have a lot of time left, but if anybody has questions, please raise your hand.
Is in Loom already async await handled? Async await? The future implementation, is it already in Loom or it's not?
Not really. So
Okay. Thank you. To keep it short.
We need to keep it short. Any other questions?
Yeah. So how much do you know about the internals of how Loom actually like builds the graph of how the like how many different options there are for the execution model?
I looks through the source code, but actually Loom doesn't create the graph itself. But so while executing the programs multiple times, it stores the additional state, I would say. So by referring that kind of that state, Loom slightly changes the condition of like which thread should we choose and kind of stuff. So by referring that state, Loom explore all states, possible states dynamically.
Do you know how the mechanism works?
Mechanisms?
Oh yeah, how it works under the hood. If no, it's fine. I'm just curious if you know. It sounds interesting.
It's kind of so of course, I saw the implementation, but I'm not sure if I all understand the internals. So, yeah.
Okay, thanks.
My question is, by how many calculation paths can be removed with those techniques?
Yeah.
Like, let's say you have 10 tasks with whose order can change. Like how much?
I didn't do like counting
Oh, right.
how much
Mhm.
how much state Loom
Mhm.
can reduce, but yeah, sorry, I'm not sure.
Oh, right. Oh, that's fine. Oh, that's all fine. But
Exact number.
you can how to say, you can reduce the time to check all states, right? Like,
Yeah.
for sure.
So there was actually other tools. I don't know much about other tools, but so without without these kind of state reduction techniques, but yeah, it took a bunch of times. So there is a description in the paper about that.
That's so interesting.
Yeah.
But I liked your presentation. I mean, yeah, like I studied model checking. I mean,
really?
yes, like when I was in college. So like kind of brought back the memories of my college days. That's so yeah, that's so great. Yeah. Anyway, thanks.
Well, we still have some questions from Motoyuki, so I will ask you our usual question. So, how did you get into Rust? I mean, how did you get into programming? Sorry, when you started, yeah.
Yeah. So originally I wanted to build my own website. So that was the first motivation of my programming life. So yeah, I used, I guess, Ruby for building my website. So, but these days I don't use Ruby so much. But yeah, I actually I like Ruby. Yeah.
Yeah. Okay. So let's go to the next one. So we really don't have time.
Yeah.
So I will just jump questions. So how did you get into Rust?
So because I had to move to another team in my company where actually Rust is heavily used. So yeah, that's why. But before, if I was interested in the Rust, so I used in my personal project. But yeah, that is a primary.
What was the hardest thing you had to learn in Rust?
Difficult thing?
Yeah.
Yeah, I think it's not specific to Rust, but this kind of multithreading or concurrent stuff is really complex. But it's not so. It's not about Rust itself. But yeah.
I see. So for the last question, what would you like the next person to present you?
So I'm mostly web space person. So I'd like to know more about like low-level stuff, where like operating systems or embedded systems. I'm not sure there are many companies that are doing that kind of stuff, but yeah, I'd love to hear that kind of low-level stuff.
Thank you so much. Thank you so much for presenting here today.
Thank you. Sorry for my bad English.